common mode rejection ratio is, so here in addition to the desired signal, some noise also will present. Is it audible now?
Yes, sir.
Okay.
Yes, sir. It's very clear, sir.
Okay. Now screen is visible?
Sir. Yeah, visible, sir. Visible, sir.
Yes, sir.
Yeah, sorry for the interruption. Okay.
No problem.
So my topic of presentation is Introduction to Biomedical Signal Processing. Myself, Professor Sheikh Rafi Ahmad. So I am working in Aicte Guwahati since 2008. So this biomedical signal processing is also one of my areas, and I also works in VLSI aspects of all signal processing, including biomedical also. This is my outline of presentation. So I want to first define some basic terms. Then I'll show the block diagram of biomedical signal processing system, the goals of biomedical signal processing system, and the problems in biomedical signal processing system, and how to address those problems. Then I'll give some examples. Basically, I'll take two important signals such as ECG and EEG. In all my presentations.
Only first slide is there, sir.
Sorry?
I think only first slide is visible, sir.
Please change the slide, sir.
Slides are not moving, sir.
Now?
Yes, sir. Now, okay, sir.
Yes, sir. Yes, sir.
So okay, this is the my contents or the outline of the presentation. So starting from the definitions, block diagram, the goals, problems, and the corresponding solutions, and some examples. Basically, I'll take ECG and EEG as two studies, case studies. Then finally, I have summary. So definition of a signal is any physical quantity that varies with time. In strict sense, it has to convey some information also. And coming for the biomedical signal, as the name implies, signal which is obtained from the physiological system such as human. And processing of biomedical signal means So all the operations or treatments we have to perform on the biomedical signals between the generation to the interpretation by the physician. So all these operations is called signal processing. If I take the block diagram of a biomedical signal processing system, so from the patient we will measure various biomedical signals such as ECG, EEG. We can have this oxygen level, plethysmography. There are a lot of parameters. Okay. So basically these signals are non-electrical signals such as biosignals. In order to convert these biosignals into electrical signals, we need a sensor called electrode. So the first the block of biomedical signal processing system is a biomedical sensor which converts the biopotentials into electrical potentials, because we are going to process the electrical potentials. So example is for ECG we will use the electrodes, EEG also will use electrodes, and depends upon the application we have different transducers or sensors. So transducer, as the name implies, transduction, changing the energy from one form to another form. Here the input can be either biological signal or it can be electrical signal. So, but the output will be always electrical signal. And another important block is here isolation amplifier, because this side of the block diagram is you have the human, whereas this side we have electronic circuitry. So if you have any mismatch in this electronic circuitry, and if any defect is there, so there is a possibility that the current will pass through the patient also. So that is why you have to use the isolation amplifier. I will discuss the details of each block in detail. So basically, as the name implies, it provides the isolation between the electronic circuitry and the patient. And we need to filter, because the signals that are recorded from this patient are very low in amplitude, and they will be corrected by a lot of noises. So because of that, we have to do some filtering and amplification. So till now we have the analog signal here. So then, because we have to use a digital signal processing, we have to convert the analog signal into digital signal. So from here onwards, the blocks which are shown in the second row, they are called digital signal processing blocks. So we know what are the advantages also, that also we'll discuss in the coming slides. So basically in signal processing means there are two operations. One is called filtering, another is called transforms. So here how to process the signals before the signal is given to the physician. So we have different signal processing techniques, including pre-processing and post-processing. Basically we have the filters to remove the artifacts. Artifact is a signal which is like a noise in case of communication system, which is undesired signal. In biomedical terminology, they are called as artifacts. There are several artifacts I will discuss in the coming slides. Then we have to use the feature extraction and the classification, like in any machine learning algorithms. This is the overall block diagram. Now in this presentation, I will take each and every block and I will explain in detail. So the first block is electrode, as I have told. I will take the two case studies of ECG and EEG. ECG, as the name implies, electrocardiogram, which is the electrical activity of heart, which represents the electrical activity of heart. So these are surface electrodes which are made by AgCl. They are placed on the surface of the body. This is something like this. Or we can have clip type of electrode also. So basically these electrodes will convert the biopotentials that are generated inside the body into electrical signals. So this is examples of ECG electrodes. Similarly, if I take totally in case of ECG, so you might have seen there will be 12 records of ECG. So out of these 12, so 6 are limb lead and 6 are chest from the electrodes, chest electrodes. So limb lead, again we have bipolar as well as unipolar. So in limb lead, normally we will take this right leg as ground. Normally this right leg will be taken as ground. So by taking this as a ground, right leg as a ground, between both the arms This particular signal is called lead 1. Between right arm and left leg, it's called lead 2. Between right left arm and the left leg is called lead 3. Similarly, if you take the differential signal with respect to the right leg, if I take the difference between both the arms or this arm and this leg, they are called AVR, augmented signals, augmented limb leads. So in this, we will take the differential signal. And these are 6 signals recorded from limb leads, and there will be 6 recorded on the chest. These are the positions. So V1 to V6. So these 12 records, the output of this electrodes will be electrical signals. And in case of EEG, electroencephalogram, so which is the electrical activity of the brain, which represents electrical activity of brain. There are different types of the electrodes are there. They are placed on the scalp. So the positions from Nasian to Inian. So Nasian is the position which is called the point between the forehead and the nose. This is the point. And Inian is the bump at the skull. So you measure this distance from Nasian to Inian and you place the electrodes at 10% of the total distance. If the distance from the Nasian to Inian is x, so x by 10 is the distance from here to here, this electrode. One electrode will be placed here. And then the first one is, this is 10%, this is 10%, remaining all are 20%. That is why this particular electrode system is called famous 10-20 electrode system. So this is 10% of this total distance. This is 20%, again 20%, 20%, 20%, and then 10%. So these electrodes will be placed by placing these electrodes on a cap, and that will be connected to the head in this manner. So in any case, the first stage is the electrodes which converts the biopotentials into electrical potentials. But the problem with these electrical potentials is they are very weak. So the amplitude is of the order of microvolts, which we cannot process unless otherwise we have to amplify, and they will be buried in noise. So you have to remove the noise before applying for the analog to digital converter. These operations you can do using digital signal processing also. Basically in digital signal processing also we are going to do the filtering only basically. But why you need this analog filters is to give a signal to the A to D converter, here to A to D converter. So the signal that is coming out of this electrode is so weak and buried in the noise, this signal cannot be applied to the A to D converter. For A to D converter, we have to give the voltage of the range of 0 to 5 volts, so that I will get the digital signal from 00H to FFH. So in order to get that 0 to 5 volt signals that is suitable for this A to D converter, we require some sort of the analog signal processing. So these first three blocks we can also call as analog signal processing. They will be performed in analog domain. Once it is converted into digital, we have digital signal processing. But in analog signal processing also we need some amplification and filtering basically. So the first amplifier which is called isolation amplifier. So in addition to amplification, this provides the isolation also. This is patient end. This is the circuitry end. We have the other circuitry here. So these two circuits are not physically connected. So the connection between this part, that is body, the patient part, and the electronic circuitry part can be by capacitive coupling. Here the coupling can be either capacitive coupling or transformer coupling or optical coupling. So we have optocouplers. So basically the signal that is recorded from this electrode is here in this side. So that will be coupled to the other electronic circuitry through either capacitors or the transformer or optical by means of the optical. In addition to that, this will provide a small amplification also. Basically isolation amplifier is the main purpose is to provide the isolation of very low level signals. So this amplification that is provided by isolation amplifier is not enough to drive the A to D converter. So the next block is the analog signal processing, which consisting of amplifiers and filters. So we basically use instrumentation amplifier. This is a instrumentation amplifier. So this is having a lot of advantages like high gain, high CMRR, basically common mode rejection ratio is. So here, in addition to the desired signal, some noise also will present. Okay, that noise will be rejected very efficiently by using this instrumentation amplifier. And in addition to that, they will be having high input impedance. Because of that, the loading effect will be less. The signal that is coming out of the isolation amplifier will be faithfully reproduced because of the high input impedance. So due to the several advantages of this instrumentation amplifier, so we'll use instrumentation amplifier with high gain of the order of 100, so that the signal will be in the range of a few volts. Now we need some filtering also. There are different types of this noises that will be encountered while recording the signal. So if I take this basic three signals, which is ECG, EEG and EMG, the frequency ranges of ECG is, it is somewhere between some 0.5 volts to up to here. This one is around some 500, 600 hertz. Whereas EEG is only low frequency, 120 or 130. EMG is having large frequency. So it starts from around some 20 hertz to 1000 hertz. But here actually what happens is the electrode offset also will be present, but this electrode offset frequencies are very less. They are below this 0.5 hertz. Okay, and then there is some noise, some more noise called 1/f noise. As the name implies, this noise will decrease with the frequency. But the amplitude of this one is very less. The only EEG signal is going to be affected by this noise. So basically, the first step is, if I take the ECG signal, this is the signal conditioning part for ECG signal. This is from the heart. Then we'll amplify by using this instrumentation amplifier, and we'll provide the gain of the order of 100. Then we'll pass through the high pass filter, which low pass filter whose cutoff frequency is 300 hertz. So all the frequencies above 300 hertz. So due to the noise, all those noises will be filtered. The output of this filter will be only 300 hertz up to 300 hertz. This will be some useful ECG range in there. And one more important interference or the noise that will be caused for the biomedical signals is 50 hertz or 60 hertz coupling. So wherever you have the instrument, there will be some casing that will act as one conductor. If any power line is there nearby the patient, that will act as another conductor, and there will be a 50 hertz signal coupling will be there. In India, it's 50 hertz, and in US it will be 60 hertz. So we have to remove this 50 hertz signal also. For that, we will design a notch filter. This will reject only the 50 hertz. The remaining all frequencies will be passed through. And sometimes we'll use a low pass filter also, whose cutoff frequency is 0.5 hertz, so that the effect of electrode offset will be nullified. Then finally you will get the ECG record. So this is all about the analog signal processing. Basically in analog signal processing, whatever the signal coming out of the electrode, we have to basically isolate from the patient. So by means of isolation amplifier, and you have to provide high gain and high CMRR, high input impedance by means of instrumentation amplifier. And you have to reject the noises beyond 300 hertz, because below 300 hertz there may be some possible the useful frequencies of ECG. If it is EEG, we will choose this frequency accordingly. If it is EMG also, so this frequency, cutoff frequency of these filters depends upon the type of signal that we are going to condition. And this 50 hertz notch filter is common to all the biomedical signals. So this is all about the analog signal processing. Now the question is, we have these filters. We can easily implement the analog filters also using operational amplifiers. Then why you have to go for this digital signal processing, digital filters? So these are the analog filters. This will act as a low pass first order filter. So I can increase this roll off ratio by increasing the order, but the complexity will increases. Similarly, high pass filter. And this is the notch filter which rejects a single frequency. So the single frequency that is to be rejected depends upon these values of R's and C's. And we have to use a to D converter to convert this analog signal into digital signal. Normally in biomedical applications we will use more precision, because in biomedical, so each and every bit value is important, because this is related to the human health. Health. In case of just image processing applications, not biomedical, so we can use even lesser number of bits also, because their accuracy is not that important. But in biomedical applications, the accuracy is important, so we have to use more number of bits. So normally we will use successive approximation type A to D converter. Now the question is, why we need this A to D converter? You can do the entire processing in the analog domain itself. We can design the filters. We can have all the signal processing, signal conditions that we are performing using digital signal processing. We can easily perform by using analog signal processing also. Then what is the need of digital signal processing? Because of these reasons. So these are the main advantages of digital signal processing over the analog signal processing. Is mainly the high accuracy. Why accuracy is high? In case of digital signal processing, we have only two levels, 0 and 1. So 0 volts and 5 volts. So if I transmit 5 volts, if I receive as 4.5 volts, that also I will take as 5 volts, because I have only two regions. So that 0.5 volts of the noise also I can neglect, because I am going to round off to the 5 volts, which is logic 1. Whereas in analog signal processing, even small amount of the noise will affect the accuracy of the system. And because of the advancement in digital technology, the digital signal processing circuitry is low cost. Another prime important of this digital signal processing is flexibility. Suppose if I design a filter with a cutoff frequency of some 300 Hz. Initially I want to process using ECG signal. Later I have decided to process EMG signal, whose frequency is some 700 Hz. So I can simply change the program. Okay? Whereas in case of analog signal processing, you have to redesign the system and you have to replace the old capacitors and resistors with the new capacitors and resistors. So in that way, the analog signal processing is less flexible, whereas digital signal processing, the change in the program or the design can be performed by means of just changing the program. So this is more flexible. And another important advantage of digital signal processing is ease of data storage. We have these memories, random access memory and read-only memories. So we can easily store the digital data. If we want to store the analog data, we need some tape recorders and all. So that is more costly. So the data can be stored in digital domain in an easier manner. Now, what are the various operations that we are going to perform on the biomedical signal in particular, or any other signal in general? So basically we have the filtering operations, transforms and correlation and power spectrum estimation, and all these are the various operations that we are going to perform on the signals. So coming for the filters, so these are the goals for the biomedical signal processing. So we have to separate the desired signal and desired signals, and you have to quantify the effect of the measuring device, and then we have to analyze the signals. These are the basic three goals of any biomedical signal processing, and for these solutions are, so the various problems in the biomedical signal processing are artifacts. So whenever you want to measure the signal, there will be some undesired signal like noise. In case of communication, in biomedical terminology, we will call as artifacts. And then there are artifacts or interference, like power line we will call as interference other than the artifact. So there are several artifacts like motion artifacts. So whenever their body movement is there, because of that, the original signal will be disturbed, and due to the non-linearities in the devices that we are going to use. So these are the problems in biomedical signal processing. To overcome these problems, so we have basically different techniques which are called the digital filters. We use digital filters, spectrum estimation techniques, independent component analysis. Basically, these techniques are the blind source separation technique, where we have the mix of the signal sources. So some sources are desirable, some sources are undesirable. So by means of these techniques, spectrum estimation and ICA techniques, we are going to divide the sources, the desired as well as undesired, based on some property. Thereby you can easily extract the desired signals. So I'm going to explain this in detail in the coming slides. First, starting with this digital filters. So filter is actually basically a frequency selective network. So this filter can be either fixed coefficient or adaptive. Nowadays in biomedical signal processing are many applications of signal processing and communication. We need to have adaptive filters rather than the fixed coefficient filters. So I'll explain the reasons. So if I take the basic fixed coefficient filter, so this any digital signal processing system can be constructed by using three basic elements: adders, multipliers, delay elements. So if I take a 3-tap or a 3-coefficient FIR filter, the expression for the output y of n is a times x of n plus b times x of n minus 1. This is previous sample, passes through the delay. Then c times x of n minus 2. By properly choosing the values of a, b and c, I can design the same filter as a either low pass or high pass or band reject with some given specified pass band frequency and stop band frequency, pass band gain and stop band gain. But normally this type of fixed coefficient filters are rarely used in biomedical signal processing, because we cannot design the ideal filters. If I design with a cutoff frequency of say 300 Hz, so there will be some roll off, so that cutoff frequency, after that also the signal will fall onto the useful range also, because of a non-ideality of the filters. To avoid this, we will use the adaptive filters. As the name adaptive implies, they adopt the coefficients in according to the situation. Okay? So in the previous case, these coefficients are constant A, B, C. Once some specifications are given, to meet those specifications, we will find the values of A, B, C and we will fix this. Whereas in case of adaptive filters, as the name implies, we are going to adopt the filter weights. Now this, if I call here as W0, W1, W2, they are also called as weights or filter tabs. They are no more constants. They also vary with the time according to some algorithm. So the one of the famous algorithm according to which the weights of the filters varies is called least mean square algorithm. This is one of the famous algorithm because of its simplicity. So in many of the applications, these LMS algorithms will be used. So as per the LMS algorithm, how these filter weights will be changed. So basically in adaptive filter, we have three operations. One is for a given input, have to find out using this formula output y of n. Once you get the output y of n, so we have to give some desired signal here. Then we'll subtract this output from the desired signal, we'll get some error signal. This error signal is going to be used to change the coefficients of the filter according to some algorithm. So these are the three basic steps in any adaptive filter. First one is filtering. See here we have W0 of n, x of n. So this W0 is a function of n. So I am writing in the mathematical expression function of n, because this will vary with the time. And this x of k I am calling as x of n. So x of n into W0 of n plus this will be x of n minus 1 into W1 of n, x of n minus 2 into W2 of n. This is filtering operation. This is basically filter output. Output y of n is given by this. So W0 of n into x of n plus W1 of n into x of n minus 1, so on up to I have taken in general L-tap filter. So in the previous case we have taken 3 taps, but the mathematical expression I have given for the generalized L-tap filter. So instead of writing this much big expression, so normally we'll use this vector notation in signal processing. So one of the standard vector notation is, so we'll use lowercase bold letters for the vectors and uppercase bold letters for the matrices. So here this x of n capital bold is there. This is called vector. Okay. So, and if you have like here E of n, they are not bold, they are scalars, only a signal. Whereas this is vector. So, I am defining this x of n as a column vector with x of n is the latest coefficient and the previous coefficient is x of n minus 1. Total we have L is the order of the filter. So, we have taken x of n minus L minus 1. This I will define as a x vector, input vector. Then W, the filter weights. We have only L filter weights, W0 of n, W1 of n, so on up to WL minus 1 of n. Now, if I take the transpose of W of n, W transpose of n into x of n, what happens? This column vector becomes row vector. So, this will multiply W0 with x of n, W1 with x of n minus 1, will get this expression. Otherwise, if I take the complement, transpose of x of n and if you multiply with the W of n, also will get the same expression. So, normally instead of writing this much big expression, we will use this vector notation, either W transpose of n into x of n or x transpose of n into W of n. This is what is called inner product. This is the expression for the output. This is the first step in any adaptive filter. Once if I know this y of n, I need some desired signal. D of n is called desired signal. So, initially even in communication systems also, before the device is tuned to the unknown signal, some desired pilot signal will be sent. Here also in biomedical also later I am going to explain some examples. So, there we need some desired signal. I will compare the desired signal with the actual signal that I have obtained. So, ideally this output should be equal to desired signal, then error will be 0. Otherwise, there will be some error. I will define this error as difference between the desired signal and the actual output of the filter. So, based on this error, I am going to vary the filter weights according to LMS algorithm. This is the weight update expression according to LMS algorithm. This is one of the famous algorithm. So, we have derivation for this weight update relation, but I have taken directly because this is one of the famous expression. So, the new weight, this is vector. In vector notation, I am representing the first expression. New weight n plus 1. N plus 1 is new weight. N is old weight. Old weight plus mu times the error that we are going to obtain here into this x of n, which is this, the input signal vector. So, if I vary this weight according to this relation, then the error is going to converge. After some iterations, the error becomes almost 0, so that the filter will be trained. Once the filter is trained, we can apply the unknown signal. So, this vector equation, this one vector equation is equivalent to L scalar equations. So, this W is vector, Wn plus 1 is W0 of n plus 1, W1 of n plus 1, so on. This is vector, and this Wn is this vector, this x is this vector. Whereas mu into E of n is a scalar. You remember that here, this W is a vector, x is a vector. After multiplying, this inner product is a scalar. Because this is actually, we are adding to a single value. Y of n is a scalar. So, y of n is scalar, desired signal is scalar. So, we will get E of n as scalar. So, E of n is scalar, that scalar we are going to take. Here this W n plus 1 is a vector, this vector. Wn is this vector, old vector, and x of n is the input vector. So, this single expression is equivalent to L expressions. This W0 is equal to mu into E of n is common. W0 of n is the first element, and the first element of x is x of n, this. And second expression is W1 of x plus 1 is W1 of n plus mu into E of n, this is common, x of n minus 1. Similarly, WL minus 1. So, here are the L expressions, but we will represent with a single expression in the vector notation. Now, these weights will be updated from iteration to iteration. After few iterations, the error becomes almost 0. Then the filter is converges. So, you see the overall block diagram of adaptive filter. We will have some desired signal, then the input which we have received pass through the adaptive filter, we will get some output. We will subtract from the desired signal to get the error. This error we are going to use to vary the filter weights. So, in summary, this is the least mean square algorithm. So, you see the output signal through this inner product, error computation, then weight updating. But here what is mu? Mu is the step size. This is going to decide the convergence, whether your filter is going to converge or not. So this filter will converges if I choose the value of mu between the range 0 to 2 by trace R, where R is the covariance matrix of x of n and x of transpose. X of n is input signal vector. This is the input signal vector. So if I take the covariance of this one, so we'll get a matrix. This R is capital letter and bold letter is a matrix. And trace R is sum of the diagonal elements of the matrix, is called trace R. Okay. If this mu value is between these values, then only this algorithm will converge. For this also the derivation in the in all standard adaptive filter books. Now what is the effect of this step size? Step size is critical here. So if I take a too small, the filter reacts slowly. If I take too large, then the resolution will be poor. That will be clear from the next graph. You see here I have plotted this mean squared error as a function of number of iterations for 3 different values of the mu's. So among these 3 mu values, this 0.0075 is the lowest value and 0.075 is the highest value. So highest value means fast convergence. This is fastly converging. But the final, it has to come to 0, but it is not coming to 0. It's oscillating at some value which is this much error will be there, steady state error. This is called steady state error. So advantages of choosing this larger value of mu is it will converges fastly, but the drawback is steady state error will be more. And advantage of choosing the lower value of mu is steady state error will be less, but it converges slowly. So it depends upon the application, whether we want the fast convergence or more accuracy, the low steady state error. Depends upon that, you have to choose the value of mu. But in any case, the mu value will be less than 2 by trace R. So see about the LMS algorithm. So this is one of the algorithms that we are going to use in biomedical signal processing. I will come to that case studies after discussing about all the techniques. Okay. So we have started with a simple filter, FIR filter, fixed coefficient filter. Then we move to the adaptive filter. Then we have some spectrum estimation techniques. These are also important to separate the desired signal from the undesired signal. So one of the famous spectrum estimation technique is called singular spectrum analysis, SSA. Here actually we will measure the signal from either ECG signal or EEG signal. This is noise corrupted signal or artifact corrupted signal. So this signal consisting of this signal, actual signal, this can be either ECG or EEG, plus A stands for artifact. S stands for desired signal, A stands for artifact. And we have measured n such signals, n such samples in fact. Then, so S is the desired signal, this can be ECG or EEG, later I am going to explain with EEG signal. Then A is artifact. So in SSA basically there are 2 stages. One is called decomposition. This again have 2 substages, embedding and singular value decomposition. Then we have the second stage is reconstruction. I will come to that in the next slide. So in the first stage, which is called decomposition. So we are going to take the single channel signal. This is single channel signal. We have n samples of that one. But we have to use a matrix in SVD. Singular value decomposition means we require a matrix. So we are going to map single channel signal, which is a vector, into multivariate signal, which is a matrix. So the values that I have D1, D2, D3, so on up to D capital N. Sorry, this is capital N, not small n. So this is D1, D2, so on up to D capital N. Okay. So using this, I will construct the matrix. This is D1, I will take as it is. D2, I will take up to DK here. Then D2 to DK plus 1. Then DM to DN. Totally, we have totally D1 to DN elements. In between, we have DK element, DM element. So what are these K and M is? Where M is called the window length, and this we have to choose according to the relation. M should be greater than the sampling frequency of the signal divided by the frequency of the signal to be interested. If it is a EEG signal, the frequency frequency signal will be around some 50 to 60 hertz. And if it is ECG signal, it's around 150, 200, sometimes 250. So it depends upon that. This is sampling frequency divided by the signal frequency. If I take the ratio, this should be M should be greater than that. That will take as window, because we have infinite data, but we have to take at any time a finite number of the samples, and that can be obtained through a window, and the window length can be decided by using this formula. So this M is this M. According to this, we have to choose. Then K, how to choose K is equal to N minus M plus 1. So we are going to map, we are going to take the N samples, D1 consisting of S1 plus A1, some signal is there, desired signal, some noise artifact is there. D2 also consists of signal plus noise. So totally we have taken capital N samples. Using this capital N samples, I have constructed the matrix which is called trajectory matrix. So the property of the trajectory matrix is, if I take this first row, second row is delayed version of this. Like that, we are going to delay, we are going to insert the new samples here, and the old samples will be lost. But this D matrix consisting of only this D1 to D capital N only, total. Now this D matrix can be treated as S plus A, because D of N is S of N plus A of N. This matrix also, D matrix is equal to S matrix plus A matrix, where S matrix consisting of the desired signal components, A matrix consisting of the artifact signals. Now the task is basically, we have to estimate the A from D. I can construct the D from the desired measurement. So from the D, I have to estimate A. Once if I know the A, from S plus A, I can subtract the A to get the S. Basically, S is the desired signal. So to get the S desired signal, I will estimate the A and I will subtract from this D signal, so that S plus A minus A becomes S. In ideal case, otherwise there will be some error here. So this is the main task is now, we have to estimate the value of A. In order to estimate this A, I will represent this D as the name implies, singular value decomposition. So this is the formula for singular value decomposition. So you might have studied this in linear algebra. So one point that I want to stress here is, for any signal processing courses, it can be biomedical or it can be any other signal processing, linear algebra, especially matrix algebra, is a must course. But normally in our curriculum, normally these courses will not be there. But at IITs and NIT levels, so this linear algebra course is must. So here, according to linear algebra, we have this singular value decomposition is, D can be expressed as Q sigma R, where Q and R are two orthogonal matrices. This is right orthogonal and this is left orthogonal matrix. The property of the orthogonal matrix is, orthogonal matrix Q is said to be orthogonal matrix if Q into Q transpose is equal to I. Or another way is, the inverse is equal to transpose only, basically. So the type of matrix is called orthogonal matrix, and this sigma is a diagonal matrix. Only diagonal elements are present, the remaining all elements are 0. So for a given matrix, any matrix can be represented in this manner. So the product of two diagonal matrix, one is right diagonal, another is left diagonal, orthogonal matrix, and then one diagonal matrix. This is one of the famous results from the linear algebra, matrix algebra. Once if I express this D in this form, then in order to find out the singular value decomposition, so I have to perform eigenvalue decomposition. We know the eigenvalues and eigenvectors. See, basically here you have to find out eigenvalues and eigenvectors of a covariance matrix C, which is defined as D into D transpose. This is the definition of the covariance matrix. This will give the similarity between two matrices. Here we are taking the signal and the time delay version of the signal. How much variance, correlation is there between these signals? Based on that, I can estimate the noise or the artifacts, and then I can subtract that artifact value. So that is why I have to compute the covariance value. covariance matrix using D transpose. D is the measured signal. This we have measured already. Then we are going to find out the eigenvalues and eigenvectors. I am calling the eigenvalues as W1, W2, W3, so on to Wm. Eigenvectors are Q1, Q2, so on to Qm. These are bold letters because vectors. These are scalars. So lowercase letters, and these are on mode, not bold. Normally bold letters will be lowercase and bold letters will be for vector. Uppercase bold letter will be for matrix. So we are going to find out the eigenvalues and eigenvectors. This you might have studied in your mathematical courses. So once if I know these eigenvalues and eigenvectors, the orthogonal matrix can be expressed in this manner. Knowing this R of k. So these are all from the linear algebra. Actually here I have taken the right results. So if you want more details, you can refer to the linear algebra or matrix algebra. Any books on this. So finally what I am going to do is this D, the measured matrix, I have expressed it as the eigenvectors into D. So this is kth element. This is the desired matrix. So this Qk into Qk transpose will form a subspace. Basically the subspace of the signal, desired signal will be different from the subspace of the artifact signal. Based on that, we can remove the artifact. We can estimate the artifact using this formula Qi transpose D. So if I follow this step-by-step procedure, I can estimate this A cap, which is equal to Qi transpose into D. D we know, and Qa we have computed using these formulas. Once if I know this A, I'll simply subtract from this D, I'll get the desired signal. This is how they are going to suppress the undesired signal in case of singular spectrum analysis. There is another technique called independent component analysis. Here basically we will have observations, n observations, and we have a linear mixture of this one. This will be well defined or well explained. The independent component analysis will be well explained by using a cocktail party. So wherever you refer to independent component analysis, this cocktail party problem is very important. So in this cocktail party, actually we have so many sources. Here I have taken n sources. This is one loudspeaker S1. This will generate a signal S1. Second loudspeaker will generate S2. Like that we have Sn. N sources are there. And here we have the mics. So here there are two, similarly we have n observations. So while what will be the input for this mic? The input for this mic will be the weighted versions of all these signals. Input for this one will be weighted version of this one. So this is called mixing matrix or weighting matrix. So the desired signal X of the observations, X will be in the form of, if I take X matrix, this is X1, X2, so on up to Xn is equal to A is matrix, n by n matrix times S1, S2, S3, so on. This is a simple problem. This I have observed. These are the sources I have passed through the matrix. This matrix will be having some coefficients. So this will be basically, you can write in this manner. X1 of t is equal to A11 of S1 plus A12 of S2. X2 of t is A21 of S1 plus A22 of S2. If I take simple two sources. So it's S1. Here in this mixing, we are multiplying this S1 with A11 for this X1 and A21 with for X2 and S2 with A21 for X1, A22 with X2. So finally you will get this type of equations. This we can measure. This is actually generated from the source. These are these matrices. If I estimate this matrix somehow, and we can measure this X1 and X2 here because these are the observation. I will measure X1 and X2 and I will estimate this mixing matrix by means of some assumptions on this unknown sources. I don't know the sources. So exactly in biomedical signal processing also, what is the problem? Here we have different sources. This is ECG signal. This is artifacts, motion artifact or any other artifacts. But here I have to observe these two signals. From this, I have to separate these two, the desired signal and non-desired signal. So for that, so I have to know some information on S1 and S2. If I assume that these are independent, I can easily estimate this matrix, mixing matrix. If I know the mixing matrix and if I know X and Y, then S is equal to A inverse X. I can compute the sources. That is the basic idea in independent component analysis. So here you said that this is observed signal. This is having mixing of two signals. So by applying the ICA, I can separate these two signals. So these two signals are generated by these two different sources. This has generated one signal, this signal of low frequency. This high frequency will be generated by this source. So the combined signal will be this. This is sum of these two signals. So by applying ICA on this signal, I can separate these two. Similarly, this also combination of these two, I can separate these two signals. Similarly, the case of sine wave and square wave, if I mix, I can reconstruct the original signals, provided you have to properly know the mixing matrix. The mixing matrix can be estimated if I know some relation between the unknown sources. The basic assumption that we are going to do here is they are independent. If this assumption is valid, then I can easily estimate the A. Once if I estimate the A from the observations, I can find out the S by using the relation S is equal to A inverse X. This is the basic idea in independent component analysis. This is the overall, this S is equal to A inverse X. Now coming for the biomedical case studies. So I will first take ECG signal processing, then EEG signal processing. So the common artifact is the undesired signal encountered in ECG recording are motion artifact. If I place a electrode on the surface of the body, if due to the respiration, there will be some body movement. Because of that, what happens is electrode will be displaced. So we will get some undesired motion artifact and muscle artifact. So due to the muscular activity, there will be some artifacts. Like in case of EEG, electroencephalogram, the muscle artifact effect will be more. Because if a person is chewing, or if a person is sneezing, so what happens is there will be some movement of the muscles. Because of that, we will get some artifact. And baseline wander. So the basic DC line with respect to which we will measure the ECG signal or EEG signal, that will vary because of the body movements. So these are common signals which are common artifacts which we will encounter in any biomedical signal processing. But the fixed coefficient filters, as I have discussed in the earlier slides, they cannot eliminate time varying artifacts. These artifacts are time varying. We don't know at what time which type of movement will be occurred in the body. So they are time varying. So we have to use time varying filters such as adaptive filters. So this is baseline wander. Basically, this is ECG signal. This is ECG signal, but the baseline is going to be wander. I will directly go for this adaptive filter. This is using adaptive filter. As I already explained the adaptive filter nature, we require some desired signal, some input signal, then error signal will be used to vary the filter weights. Here in ECG signal, in order to remove the motion artifact, this is undesired signal. The motion artifact signal we are going to apply at P1 of the signal, and at D1 desired signal. This P1 is nothing but this here. Okay, and here we are going to apply the sum of the signal, actual ECG signal plus motion artifact signal, and X of n will be given to the simply noise signal. You see, observe here, this signal is actually sum of signal plus noise, and this signal is only the noise P2 of n. This is somehow related with the P1 of n. I can measure this from the other part of the body, because mostly this noise will be throughout the body almost constant. So this is noise corrupted signal, the desired signal plus noise. This is only noise. If I apply this, after the convergence, what happens is we have some mathematical derivations. I'm going to skip all those things due to the time constraint. So here at the convergence, what happens is, so the filter output is approximately equal to P1 of n. This filter output is at the convergence approximately equal to P1 of n. So if I subtract this is actually S1 plus P1 and we are getting this as P1. So if I subtract P1, the output will be here, you will get signal. So we are going to try in this such that this signal is signal plus noise. Till the output of this filter is noise, which is P1 of n, I am going to iterate this filter weights. So at the convergence, this y of n becomes P1 of n, and this d of n is S1 of n plus P1 of n. Output will be this P1 of n, this P1 of n will be get cancelled because this is minus, this is plus. So we'll get here the desired ECG signal. So this is the basic theory to eliminate the motion artifact from the measured ECG signal using adaptive filter. And we have formulated some, we have carried out some simulations also, and we have shown the result. So how a particular algorithm will will remove the artifacts. So for that we have taken a lot of variants of this LMS algorithm. This is basic simple algorithm is this Wn plus 1 is equal to Wn plus mu into E of n x of n. This is basic algorithm. So we have a lot of variants of this algorithm. So these are the different variants of this. We have applied all these variants and we have studied which algorithm is most suitable for removal of motion artifact from desired ECG signal. And I'll show some simulation results also. So only this weight updating expression for normalized LMS algorithm, all those algorithms will be different. These are the different weight updation expressions. They are slightly different from the conventional LMS algorithm. So these are basically the simulation results. So this is the noise corrupted signal. This is having original ECG signal plus motion artifact signal. Original ECG plus motion artifact. So here after passing through the filter, this is recovered signal if I use only LMS algorithm. You see here the motion artifacts is removed here. And if I use NSR LMS, which is normalized sign regression LMS, these are all variants. This is the, so in any case we are going to remove this motion artifacts. So in all these cases motion artifacts is removed, but there will be small difference in terms of the signal to noise ratio that we cannot observe from these plots because all these plots looks like similar. Okay, so to have this differences between these four curves using different four different algorithms, we define some matrices such as what is the mean square error and what is signal to noise ratio. These are the important metrics that we are going to use to decide the superiority of a particular algorithm. Similarly, this is for the muzzle artifact. This is for the motion artifact. This is for muzzle artifact using different algorithms. So these are the signal to noise ratio values using different algorithms. So among this, so these are different records. This ECG can be taken, this ECG we have taken from this MIT database, which is the famous database for ECG. And in MIT database we have different records. We have considered the 100 record. The explanation of each record is given in the database. So we have taken a different signals with different characteristics, and we have find out this error using different algorithms. You can see that the error will be less in this case. So this is one of these measurement results. Then so I'll discuss the second signal, which is EEG signal processing. EEG is very important for detection of the epilepsy. Epilepsy is a neurological disorder which causes the seizures. So the person will be lose his conscious. Okay, so seizure. So whenever seizure comes, this type of EEG will be recorded. And in some cases, this EEG can be used for sleep splendor clarification. This is rapid eye movement. So some persons will be having habit of, rapid eye movement. These things can be measured through the ECG. And one other important, very, very important application of the EEG is nowadays we are using this, which is called brain computer interface, BCI. So using this, brain activities. So by thinking and all, we can activate some operations. This is brain computer interface, BCI is one of the very recent area. So in this, basically we will take EEG signal, which is corrupted by noise. We will do some pre-processing, then feature extraction, classification. These are the main techniques in any, post-processing systems. Pre-processing is basically filtering and removal of the noises. Then you have to extract the features, and then you have to classify which one is the desired signal, which one is the artifact. So these are the different works I have done. This is actually done by one of the research scholars who completed the PhD, and now he is doing postdoctoral studies at Korea. So the first work he has done is, so motion artifact removal from the single channel EEG. The challenge here is, as I was told in the earlier slides, normally we will use a 10-20 electrode system. Means totally lot of electrodes, nearly hundreds of the electrodes will be placed on the scalp. But it will cause uncomfort to the patient. So to avoid that, what we have used is, we have used only single channel, only single electrode at the center of the cerebellum. So we will take the single electrode, we will pick up only single ECG, single EEG. We will process that to remove the artifacts. So in that way, this will reduces the complexity of the system. So in earlier system that I have shown, 10-20 electrode system, lot of electrodes will be placed around the skull. Whereas here only single electrode at the center of the cerebellum. Because of that, lot of complexity will be reduced. But the problem is the accuracy. So if I record lot signals, I can easily remove the noises and I can easily interpret the brain activity. But here, because you are measuring only single signal, so there may be chances of less accuracy. But to overcome that, we have used different signal processing techniques. So basically SSA, which I have explained earlier. So I will record this n, x1, x2, so on up to xn, total n samples of the single channel at a different time instance, at a t, 2t, so on up to nt. So those signals, using those signals, as I have told, the first step is conversion of this single channel signal into multivariate signal matrix. This matrix consisting of this S, which is EEG signal, and A is artifact, which is motion artifact. This is embedding. This process is called embedding. Then we will find out the covariance matrix. Then we will use the local mobility criteria. This is our novelty of the work. Here we have used the local mobility of the eigenvalues of this covariance matrix. Once if I know the eigenvalues, so the basic this thing is local mobility. So we are going to define the local mobility as the ratio of the eigenvalues of this vector to the previous vector. Okay, which is called as F1 by Fv. So once if you know the local mobility, one of the important result here is that this is the spectrum of the signal. In this, there are some desired signals, there are some undesired signals. So these low level signals. So one important criteria is the local mobility of the motion artifact is less than the local mobility of the EEG signal. So how to find out that? For that we have fixed a threshold. How this threshold will be decided? So we have chosen this threshold as 0.1. So all the signal components which are above this 0.1 will call as EEG signals. Below this, only this component is there. This is called the motion artifact. How this threshold is decided is, normally the motion artifact, the highest frequency of the motion artifact is 4 Hz. So we have taken a 4 Hz sinusoidal signal and we estimated the amplitudes. From that we fixed this threshold as 0.1 millivolt. So we will fix this one. So we have recorded all these components. Out of this, only one motion artifact signal is there, this one, and this one is also motion artifact, which is almost 0. It's not visible here, but it's not 0. It's a small value which is less than 0.1. So these two are motion artifacts, remaining all are signals. So I can easily distinguish between the actual EEG signal and motion artifact. So once if I estimate this artifact, I can remove from this S plus A, this A, so that I will get S. This is the desired EEG signal. This is the basic principle in SSA. So based on this SSA, we have carried out some simulations. These are the simulation results. And there are some earlier works also. We have compared with earlier works, and we have shown that I have not shown those table here. So we have got good SNRs and less MMSC when compared with the existing works. So another criteria is instead of using this local mobility of the eigenvectors, another thing is this motion artifact will be having the frequency spectrum. The maximum frequency of motion artifact is less when compared with the EEG signals. So by measuring the peak frequency also, we can distinguish between the desired EEG signal and motion artifact. We will fix some threshold similar to the local mobility. So if the signal frequency is above the threshold, it is EEG signal. Below the threshold, it is due to the motion artifact. In that way also we can find out. So it's observed that in case of low to medium muscle contraction, the muscle artifacts will be in this frequency range. And in case of high muscle contraction, the motion artifact will be in this range. So accordingly, you can fix the threshold. So if the threshold values, if the the frequency of the measured signal is above this threshold, it is the EEG signal. Below this threshold, it is motion artifact. So these are some results. We have got the complexity of this, our signal is also less. And in terms of signal to noise ratio also. So this is percentage of mean square error. We have got good mean square error. This is comparison with already existing work, which is called empirical mode decomposition and CCA technique. So we have got the proposed technique is faster than the previous technique, and we have published this work in Elsewhere's journal on biomedical signal processing and control. And the second one is eye blink artifact from the EEG. We have to remove the eye blink. While measuring the EEG, eye blink is one of the major artifact in case of EEG. So this we have removed by using the adaptive filter, which is called as adaptive noise controller ANC. So we have used the adaptive filter and we have used SSC also. We combined these two. So earlier there was no technique which combines this SSA and ANC. So using SSA and ANC, we have removed this eye blink from these EEG signals. So there are some important results. So there are some previous technique which is basically DWT ANC technique is already existing. So when compared with this DWT ANC, so these are the mean absolute square errors of the proposed technique. This is SSA ANC is our technique. You can see that there is a lot of decrease in the mean square error. This is 0.43, this is 0.19. So here also, so average we have almost 1/4 or 1/3 of the error is less. And here if I take in terms of these waveforms also, we can easily detect these seizures. Basically this we have applied in a seizure detection technique, where the seizures which is undesired neurological disorder that we can remove from the desired EEG signals. This is the second work that we have carried out. And to have the real-time implementation of this one, because the signal that is going to be applied here is a single channel signal, which is single signal, but here we want to use SSA. SSA is basically it works on matrix. This is multi-signal input. So this single channel input is going to be converted into parallels using a serial to parallel converter. We will store in a buffer. Then we will give NN samples at the same time. As you have already seen in the mathematical formulation, SSA will process N samples. But here at a time we can measure only one sample. So we will store these N samples in a buffer using the serial to parallel converter. We will give to SSA, and SSA give again N samples at the same time. But ANC is a serial device. It works on single sample. So we require a parallel to serial converter. We will remove the noise, again parallel to serial converter to give the desired signal. We know that the adaptive filter requires a desired signal. So the desired signal and input signal will be obtained from these buffers through this parallel to serial converters. We will perform this. Then we are going to estimate this noise signal, which will subtract from the noise corrected signal. So this work we have published in IEEE Sensor Journal. There is one more work carried out. So this is ICA technique, as I have discussed in the earlier slides. ICA is also one of the technique which separate the sources. So from single channel, we have used the ICA technique, and along with SSA. So basically we have three works. In first work we have used SSA, in second work SSA with ANC, in third work SSA with ICA. So here using this SSA, we will divide this 0 to Fs by 2 into 0 to Fs by 4, Fs by 4 to Fs by 2, then again this into 2 halves, this into 2 halves. Like that here, using ICA we will get different components. This is signal and this is artifact. So this is the block diagram of the work that we have carried out. We have taken a single channel signal. Basically, we have decomposed into two equal frequencies. Again this into two equal frequencies. Again this into two equal frequencies. Like that, we have taken a multi-channel signal that I have applied to the ICA. This basically will separate the signal and noise by properly estimating, by properly assuming that these signals are independent. If I estimate that A matrix, mixing matrix, I can find out the sources, signal as well as artifact. So these are some simulation results. Again here, it's actually difficult to make the justification from these graphs, because this EEG and ECG signals, all the signals looks like similar. So we have the matrices, we have to depend upon the matrices only to decide the superiority of a particular technique. So there are some results. So we have got here also a good signal to noise ratio and less mean square error. So this we have published in IEEE Transactions on Instrumentation and Measurement. So there is a fourth work we have carried out. So which is muzzle artifact removal to detect the seizures. Okay. There are some results in a similar manner. This also we have submitted to this IEEE transaction on affective computing. So these are the four works that has been done by one of the research scholar. So based on these four works, he got the PhD degree. So this is about some studies on ECG and EEG. ECG also I have some publications. You can refer to my website. So basically this is the conclusion. So I have started with the block diagram of the biomedical signal processing system. So before A to D converter, we have some analog signal processing. I have discussed the various blocks. After that, digital signal processing, I have discussed basically the adaptive filters, the singular spectrum analysis, and independent component analysis. These are the three different techniques we can use to efficiently remove the artifacts from the ECG and EEG signals. And in the latest, one of my research scholar, she also completed PhD, but she is working on wireless body area networks. This block diagram that I have shown earlier, we can fabricate a IC which is of the size of just 1 rupee coin. The entire circuitry, all the techniques that I have discussed till now, we can fabricate in a IC with a size whose size is almost equivalent to 1 rupee coin. Okay. So I have done some VLSI works also on this, and one of my research scholars, she has completed on wireless body area network. So which consisting of a transceiver, which is transmitter as well as receiver for monitoring the various biological signals. Okay. So this is from my side. So if you have any doubts, you are welcome to ask.
So, sir, good morning, sir.
Good morning,
Rafi, sir.
Yeah.
So thank you very much for your wonderful talk on this biomedical signal processing, sir. I request to all the participants, if you have any doubts, you can ask to sir, sir. Sir, any doubts, you can ask, sir. Unmute your device and you can talk. Otherwise, raise your hand. Any doubts? Yeah. Anu. Wait, madam. Yes, madam. You can talk, madam. Anu, madam.
Sir, how can we like on which hardware we can implement such kind of adaptive filters, sir? Shakes, sir?
Sorry.
On what kind of hardwares we can implement such adaptive filters, sir?
We have like we can implement the filters using the multipliers and adders only basically. Adaptive filter also consisting of multiplier adder, and then we have some lookup table type of thing. I have a lot of publications, nearly some 6 to 7 IEEE transaction papers on implementation of LMS algorithm. You can search in IEEE also. Otherwise, if you want, I can send also those papers. So I have done, plenty of work. Two of my research scholars has got PhD degrees out of this LMS algorithm VLSI architectures. You can use lookup tables basically, and they can use efficient multipliers and various VLSI architectural optimization techniques.
Sir, can we use microstrip in that for making such kind of filters? Microstrip lines like distributive circuits and kind of.
That will be at high frequencies, but biomedical signals are very low frequency.
Okay, sir. Yeah, actually.
Sir, unmute your video, sir. Rafi, sir.
Actually, the problem is my audio and video are both, because the audio is not working.
Yeah,
so
yes,
video, actually that camera only, there is some mic is there. I am using that mic actually.
Yes, sir. Yes, sir. Yes. Any doubts from the participant side?
Sir, one more doubt in the chat box, sir.
Yeah,
Will
you
there
can ask
be
me.
artifacts due to power supply?
Yeah, that I have discussed now. We can have notch filter. We can remove using notch filter. It's basically 50 Hz only. I have to reject only 50 Hz signal. I can design a narrow band reject filter which can reject only single frequency 50 Hz.
Yes, sir. Any other doubts? Any doubts? Any doubts?
And sir, what kind of softwares for simulators?
Otherwise, you can post in the chat box. If you have any doubts, you can post in the chat box.
Basically, I am using only MATLAB only. So if you want to use some deep learning techniques, you can use Python also.
Yes, sir.
And if you want Verilog, VLSI implementations, then you have to use Verilog or VHDL.
Yeah, one more doubt, sir. Can you implement the entire system of ECG using FPGA?
Which ECG?
So can we implement entire system of ECG using FPGA?
Yeah, sure. So entire system of ECG, noise removal system. Basically, ECG means just will record, that will be having some noises. So all these techniques, independent component analysis, we have FPGA implementation, we have SSA, we have FPGA implementation. All these algorithms you can implement by using FPGA also.
Praveena madam, you can ask madam.
Yes, sir. Sir, good afternoon, sir.
Good afternoon.
Sir, actually, you are telling that in one single channel, EEG signal can be captured like that, sir.
Yeah.
That only you can. But what about the accuracy, sir? Because 16 channels or some 24 channels we are going to measure.
So that is why actually we combined two techniques like SSA and ICA, SSA and adaptive filter. So
okay, then even one single channel also will get, sir.
Yeah.
In that case. Okay. Then generally minimum channels will be there now, sir, for measuring the
many
scale.
channels around the skulls, nearly hundreds,
yes,
means not hundreds, even 20 electrode system, nearly some
yes, sir.
50 or 100
Yes,
electrodes.
sir, minimum 24 they are telling.
Yeah.
Yes.
So another problem with that multi-channel is again complexity is more. It will cause uncomfort to the patient. But there are some applications where we cannot connect those many electrodes also. Suppose a sports person is there. I want to study his fitness. So while he is doing exercise, his normal activity, I have to record. With these many electrodes, he cannot do his normal activity. If it is a single electrode, he can do his normal activity.
Okay, with single electrode also we can capture and we can process, sir.
Yeah. Especially in that sports,
Yeah.
I mean, to study the, the fitness of the sports person and all, there actually this technique is very much useful.
Okay, thanks.
Any doubts from participant side? Any doubts? Okay, I think no doubts from participant side, sir. Thank you very much for accepting our invitation, sir. Rafi, sir.
Thank you.
Nice presentation, and it is very informative. Thank you so much, sir. Any reference matter? One more question, sir. Any reference materials?
I told no, actually based on this works, I have nearly some 5 to 6 IEEE and elsewhere journal papers. So that if you have access, then you can download. Otherwise, you send a mail, I'll attach those papers.
Yes, sir. I will share your mail ID, sir.
Yeah.
Yes, sir. Sir, one more doubt from participants, sir. Is it possible to use ANN or deep learning in removing the artifacts?
Yeah. Now, one of my latest work has been published in one of the conferences in Malaysia. That work actually I have not presented here because that conference is in a few days later is there. We have prepared so these slides also. One of the latest work nowadays everybody is using this DNN and ANN, all those things. That is also possible.
Yes, sir. Any doubts? Otherwise, I will close the session, sir. Any doubts from the participant side? Madam, you can conclude, madam. No doubts.